Okay, so this is going to be for 3.6, and this will be inverse functions. So an inverse function is a reverse function. It gets us back to where we started. So I go to school, the inverse, I come back home. So wherever I start from is, if I apply the inverse function, I come back. So the inputs and the outputs switch places. So notice I go from home to school. The input is home, the output is school. On the return journey is the opposite. Input is school, output is home. Okay, so we're going to look at various inverse functions. So formula that determines the perimeter of a square is P equals 4S, right? Because you've got four sides and all the side lengths are the same. So S plus S plus S, which is 4S. So what they get involved in determining the side length S when P equals 20. So we know 20, what we're doing is we would need to divide by 4, right? 20 divided by 4 would give us a side length because 20 is the length of all four sides added together. Okay, and so yes, take 20 divided by 4, we get our 5 inches for the length of a side. So this is kind of a reverse process. We're usually what we're starting with is they give us a side, we're getting the perimeter, right? That's what's going on. But if they start with the perimeter and we want to get the side, it's like that example. We're starting at school and we need to go home. So it is an inverse process. And so we could practice basically this one to find P. We're dividing each of them by 4 rather than multiplying. And so yes, division and multiplication are inverses of each other. So let's have them work through a few of these. 36 divided by 4 is 9. 2.2 divided by 4 is going to be what, like 5.5, 5.5 inches. 100 divided by 4 should be 25 inches. Reverse process. Read through that. What did we do? We used division instead of multiplication. So this is the idea of inverses. If we have a process that's adding a number, the inverse would be to subtract, and vice versa. So those are inverse operations. Gets us back to where we started. So, generalizing it. Let's see what they're talking about. Well, we were thinking if I know the side length, right, I had to multiply by 1/4, or I had to take it and divide it by 4. One of these two. That's what we have to think through. Okay. The two are related because they are inverse functions. If you give me the side length, I can get the perimeter. If you give me the perimeter, I can get you the side length. So they really are getting us the same relationship, just starting with different inputs. The input of one gives us an output, and the output of the other is the input. So the inputs and outputs are changing places. However, they're the same thing, right? If the perimeter is 100, side length is 25, and the same thing's going to happen on the other side. So that kind of partnering is going to work. So we basically, this all says is we call 1 to be the dependent value. So 2 is the input, and then when we look for the inverse, we would say, so generally we'd call this x, right? And then we'd say y is equal to whatever the output of the function is. The inverse function is going to switch places between these inputs and outputs. Okay, so let's think of this as a process. If I know the side length, I put it into the function, I take 4 times s, and that's going to give me my perimeter. Okay, so we can do any particular value into the function machine, right? The function will take whatever the input is, 8, so that's a side length of 8, multiply it by 4, and it will tell us that we have a perimeter of 32 inches. So how is f of 12 processed? Well, 12 goes into the box, multiply it by 4, and that gives us the perimeter, which is going to be 48. 4 times 12. That's the whole process. If we start with the perimeter, the box is a little different. What happens in here, instead of multiplying by 4, we're dividing by 4. So we're getting an output, a slightly different function, g of p, that we get the side length. We do this by, we use some new notation. Let me put it this way. So we do this, looks like f to the minus 1, but this is not an exponent. We call this f inverse. This is just, which is a little confusing, right? Because it looks like a negative exponent, but it's not. We'll address that a little bit more later. And so g is the inverse of the f function. We start with f being, give me the side and I'll give you the perimeter. G is taking, well, no, if you give me the perimeter, I can give you the side. And so I can relabel as, hey, there is a connection. I could just say, well, G really is, like, let's call it F inverse instead of calling it G. Let's give it that name. So what I would say is F inverse of P gets us back to S. So if I evaluate G of 32, now remember that's the one where I'm dividing by 4. What is processed? I take it and divide by 4, so then I'm getting the side length is 8. Okay, so G is the function. The inverse function could have just as easily listed this as, let's find the inverse of 32. Now, that's where the inverse function is kind of more meaningful, since we know that the forward function, f of s, is simply taking 4 times s. The inverse one, we're going to divide by 4. Okay. So they're related because they're inverses. And again, you can think your way through it. What do you notice about how the input and output qualities for f and g are related? Well, they give us ordered pairs, and again, for f, the input, say, was 8, side length of 8. The output would be 8 times 4 is 32. Over here, this inverse function, the input would be 32. The output would be 8, and so we get an ordered pair 32, 8. So notice how the ordered pairs just swap. Change places, really. That's what an inverse does. So again, here's an explanation that can be given. And here's another one. Input quantity of F is the output quantity of G, right? They're just changing places. Very wordy, but that little example with the ordered pairs, and if I just wrote them a little bit smaller, so 8, 32, 32, 8. That's what's going to happen. Okay. And I guess we could put, this is inches. Well, they're both inches, but this is side length, perimeter. This is perimeter, side length. Okay. And again, we could go through each of these, defining f and g. F is a function we multiply by 4. G is a function we divide by 4. Watch what's going to happen in each of these is we're going to end up with right back where we started. So side length of 5, we put it in this one, we get its perimeter. put the perimeter in a G, you get the side length. It's going to be 5. And the same thing is going to be with all of this. Start with the perimeter. This function will give us the side length. Input it into F, you get back to the perimeter. Okay, and it's kind of cool, I guess. You know, you always get back to where you started because you're doing the inverse. You're inputting the inverse function into its function it came from. You're going to school and coming back. Whichever way you want to look at that, you end up back wherever you started the process. Okay, and that's always what happens with an inverse function. Yeah, so yeah, true. One function undoes the other function. It's almost like nothing happened. There was a journey in between, but if it happens fast enough, you just didn't know it. The process, well, always do opposite operations, right? Multiplication, the inverse is going to be division. Division, the inverse is going to be multiplication. And again, you'll see addition and subtraction are paired in both ways. And input and outputs switch places, right? The input quantity of F is the output quantity of F of it. So again, also you're going to see domain and range will switch places. See how much further we have to go. Step by step we make it through. So I just keep going. Yeah, just enough time. Okay. So one of the ways of doing this is if you've ever traveled internationally, anywhere outside, most countries will use Celsius or centigrade. I know that's what they used to call it, since Celsius is instead of Fahrenheit. So if you know the Celsius, you do this process to figure out how hot it is in Fahrenheit or cold it is. Should I have a jacket? Should I wear shorts? All that kind of things. One thing I always do, so we'll talk a little off track, but mathematically 9 out of 5 is almost like 10 out of 5. It's a little bit smaller, but you could do this estimation. Celsius is almost 2 times as large as Fahrenheit. But the starting value, where the zero temperature is 32 degrees off, because water freezes at Fahrenheit 32, and Celsius is set up that at 0 is when water freezes. So there's kind of a different starting point, and then it's about a difference of 2. Again, there's a little bit of an error when you do it that way, but it gets you close enough when you think about it. So one way to do it is just take whatever, if it's 30 degrees Celsius, take it times 2, that's going to be 60, right? I can do that in my head, and then just add 32 to it. That's going to be 92 degrees. So that's the useful way. Okay, it's going to be kind of hot today. Certainly don't need my jacket. But when I heard it was 30 degrees out, I might have started thinking, that sounds cold. But do the arithmetic, and again, thinking of doing it in a way that that's useful. Same way you might have people visiting from any other country but the US, and they want to know how hot is 120 degrees, right? It sounds really hot to them, but you could do the same process. So in that case, we will do the opposite, and that's what we're going to work through. We would subtract 32 first, and then again, for just an estimate, you could divide it by 2, and you get close enough. Get close enough. Now, if you're doing a baking recipe, it might be different. Okay, so if you want to switch it, right, you subtract 32 from both sides, and then you invert it. So this is 1/2. So if I know the Fahrenheit, subtract 32 and then divide it in half. So 120 degrees would be something about 90. Take 90 is going to be about a 45. Again, we made some quick adjustments, but these two are inverse relationships. So instead of adding, we are subtracting. The other thing you see is that the order of operations has changed. We're doing the subtraction first and then the multiplying, whereas up here we did the multiplying and then the adding. And notice we're multiplying by the reciprocal of 9/5, 5/9. So, the difference between multiplication and division inverses. Define a function g that determines the temperature in degrees Fahrenheit in terms of the temperature. Now, there's a function. We just did that. All we're going to do is, instead of saying c equals, we're going to say g of c equals, right? G of c equals this function here in terms of temperature in degrees Fahrenheit, in terms of, so if you give me a Celsius, we can directly get it this way. H is the temperature degrees Celsius in terms of degrees Fahrenheit. So this is, again, we would solve this for Fahrenheit just like we did before. So subtract 32 from both sides. There it is. Multiply by the reciprocal. So we've got the inverse function. G of C represents temperature in Fahrenheit. H of F represents temperature in Celsius. Okay, so and so G of 100, that means it's 100 in, I forget which one was which. Yeah, that's what I said. So this is in Celsius, which is pretty hot, be 212 Fahrenheit. Hopefully that's in like an oven or something. H of 212 is going to get us back to 100, right? Because this input gives us that output. This input is going to give us the 100. So we see how that works. They're inverses of each other. So H of G of 100 is just going to be 100 because, there was an intermediate step, but it undoes each other. Same thing with G of H of 212. We end up back exactly where we started. So if we're doing this one, we've got a function. Solve this function for r. Now, I've seen some of you doing this as homework. What we want to do is just solve this one for r and explain what this new formula represents. So we do go ahead and solve it for r. And so we multiply by 3/4, right? That comes over. There's our 3/4. And then we divide by pi, so that's why the pi is up and down in the denominator. So that all comes over first. And then to get r cubed, we need to use a cube root, which we do, so we can solve it for r. This formula determines the radius of our sphere in terms of inches. So if we know the volume, we can find the radius. Before we were doing this with a graph. We looked up on the graph. Here's the volume. What kind of radius does it have? We can also use this formula. So this is a function. Again, this is just what we just did, but we're going to use function notation now. So G of E, there it is. G of E really is r. So it's just replacing the r with function notation. So what is f of 40? F of 40 means we have a radius of 40. That's going to give us the volume. G of 40 is saying we've got a volume of 40. What is its radius? F of 40 represents the volume. G of 40 represents the radius that has a volume of 40. So those are two different things. We could go ahead and calculate. This is saying when you've got a radius of 7, you're going to have a volume of 1,436. This one's saying when you've got a volume of 2.14 cubic centimeters or inches, we're talking about inches here, that the radius would be about 0.8 inch, so less than 1 inch. So radius gives us that volume. That volume gives us that radius. That's what the two functions are doing. So we kind of did this earlier. We did it with a graph. So we could talk about this. What's the meaning of f of 6? Well, 6 is the input, and it's giving us an output of 288 pi. So it's meaning that a volume of 6, or sorry, a radius of 6 gives us a volume of 288 pi. The other function takes that 288 pi as an input, and then it's going to get us back the radius. So we notice how those two are connected. F of 6 gives 288, g of 288 pi gives 6 inches. Inverse functions. And so if we take a composition of inverse functions, right, we start at 6, we're going to do something to it, but then we're going to undo it, we're going to end up right back at 6. So as soon as we know that we're doing a composition of a function and its inverse, we always know we end up right back where we started. Now yes, you can go through and do the math and get the intermediate and then do that and get there, or you just say, hey, I know these guys are inverse functions, I'm just going to go back to where I started. One's going to undo the other. So a formal definition, what is an inverse function? It undoes, one function undoes the other. So that the inputs and outputs are related because the input of one is the output of the other, and the output of one is the input of the other, right? They have to have that relationship. And they undo the process. So G undoes F, F undoes G. I always think one thing I like is like you might have to dig a hole. That's one process. The reverse process, the inverse process is to fill the hole back up. Now, you notice that once you dig a hole, the soil's a little bit looser. You generally either can't get it all back in or put it all back in, but it's not exactly the same. But mathematically, what we're looking at is relationships that end up being exactly the same. Inverse functions. So one way we can go about this is if we have it, solve for the formulas for the variable in the formula. So solve this one for x. So we're going to add 8 to both sides and then divide by 2. Right? First add 8 to both sides and then divide by 2. We'll multiply by 1/2. We have now an inverse function. Multiply both by 4, so notice we're going in the reverse order, because up here we would take r plus 19, then divide by 4. In the inverse, we first multiply by 4 and then subtract 19. And we're going to see the same thing here. Now, the variable's down in the denominator, so we're going to have to get it to the other side as well. So we're going to see things kind of have to sort of flip-flop around. So the way I would do this is maybe multiply both sides by x, and you get mx equals, I've got an x down here too. Well, I think I'm going to leave this. They're going to, I think there's a typo here, but we'll leave it be. Leave it be. Okay. So part of this is, again, a lot of reading, but the main part that we want to focus on is this interval notation, or sorry, not interval notation, inverse notation. F inverse of y equals x. So if y equals f of x, then we can call the inverse function f inverse, and we use it with this little -1 up here. Notice that on the inverse, the input is the output from the original function, and the output is the input from the original function. Okay, and this is where they're talking about, yes, a negative exponent does equal, if it was an exponent, it would be 1 over n, but this is different. This is saying this is not, right? It's not true. This is not true. We're referring to it as just inverse. So don't ever, when you see it this way, function notation, just say F inverse. That's what we want to see when we have this. We'll call it F inverse, G inverse. We don't want to say the other one, so I won't say it. Okay? There we go. So if we want to define a function, right, this is going to be x equals F inverse of x. So we're going to have to solve this to think of it as y equals 3x minus 7. We're going to add 7 both sides. You get y plus 7 equals 3x. Divide both sides by 3. So this is our inverse function, right? This is what x equals divided by 3. So we're going to say F inverse of x equals, oh wait, I messed up, F inverse of y. So y is the input, right? And we get y plus 7 over 3. I'm going to clear it out and let them work through it. The inverse is 1/3 y plus 7, or y plus 7 over 3 like I had it. That's the inverse function. Now, the same thing's going to happen here. And again, what you're going to want to do it over here. Think of this as w equals 2r minus 5 or 6. We want to solve for r, so we multiply both sides by 6. 6w equals 2r minus 5. We'll add 5 to both sides. 6w plus 5 equals 2r, and then divide both sides by 2. So r equals this. This is the inverse function. So we can now talk about j as being the inverse function with w as the input, right? And r is going to be the answer. And so it's going to be 6w plus 5 over 2. 1/2, 6w plus 5, that's our inverse function. Now, using a table, so f of 0, so we'll go down to x equals 0, f, oh wait, yeah, x equals 0, f of 0 is going to be 4. G inverse of 3. Now this, what we do is we look at the g function. Remember, this is the output. So the way we read this is we come and find when the output is 3, and we're looking at the input. So in this case, it equals -1. G inverse of 0, we come down here until we find the output of 3 for g, because it's not the inverse, right? So then we read that input. And finally, f inverse of -1, we come through the function until we find the output of -1. It's kind of like we're looking it up backwards, right? That's what an inverse function does, it comes backwards. And I think this is 4, -1, 3, -1. First one was the only one that worked, sort of looked it up in forward motion. The x, the input, get the output. The other one, we look at the output and then we get the input. That really goes on with an inverse function. And what we found is already, we built this up, is when you take a function and its inverse and you do a composition, you always get back to where you started. So f of a plugged into this is always going to give us what we started with. It's just some value in between, but then we get back. And it doesn't matter the order you do it in, wherever you started. Notice this one's sort of different. The f inverse, we started with b. Remember, it's the output, gives us f of a, gets us back to b. But the bottom line is wherever you started, wherever you started is where we connected. Because that's what an inverse does. We do it and then we undo it. Or we undo it and then we do it. So however you want to think of that, it's a process where you start here, you go there, and then back. It doesn't matter where we went, it's we always end up right where we started. So how can we prove whether these are inverses of each other or not? Well, we could do the composition and see what it works out. So composition, what they're going to do is they're going to start with this as a function, and in for x, they're going to plug in this. And watch how this all plays out. Hopefully we do it step by step. They don't. But, so we're going to take f of x and put it in here. And it becomes this whole thing here. So a negative and a plus 8, that is going to undo each other. And so that's 0. We've got that, so that cancels out. This is what we're left with. 2 goes into 2, that's what we're left with. And then we get a plus 1 and a minus 1, but those cancel out. We ended up back exactly where we started, right? We started at x, we ended at x. That's the idea of a composition or inverse functions. Now to really prove that they're both inverse functions, we also have to show that it works the other way. We have to go f of f inverse of x, that this also equals x. Occasionally you get one that will work in one direction, but one sort of does it, but it doesn't. Those are very rare though, but they do occur. It's possible. It really has to work both ways. Try it again. This one, so I'm going to plug this one in for x, and then we're going to see this time I'm going to take a 4 and multiply by 3. I'm going to subtract the 7. So right, so the 4 cancels out, and you get 3x plus 7 over 3. By both. Yeah, see, it looked like it might be, but we didn't end up with just x. We got this little extra. We didn't end up where we started. So in the verification process, because you can't just take 3, go into 3, and then have a 7. Yeah, see, these 3, you can't cancel it. Maybe you thought you could, but you can't, because the 3 has to distribute to both parts. So in this case, we don't have an inverse, because we did not get back to where we started. We started at x, we did not end at x. We ended up with x at minus 14 thirds. A little different place. And so Sarah gives Maria a 30-yard head start, starts running. Once Sarah starts running, she travels at a constant rate of 4.5 yards per second, and Maria goes at 3 yards per second. A little bit slower. So, yeah, head start, 3 yards per second, 4.5. So Sarah's faster, but she's got to make up this 30-yard difference if she's going to be able to finish first. Okay? So how could we model Sarah's lead in terms of t, the number of seconds since they began running? Well, remember we start with 30. The lead's going, since the difference between their two is 1.5, right? 4.5 minus 3. That's how the lead, the difference, the distance between them is changing with each second. Sarah is getting 1.5 yards closer. Okay, so the distance between them is shrinking. So what would be the inverse function? Well, it would be 30 minus 1.5 d. It's going to give us distance between t. We solve for t, so subtract 30. That's the part there. And then divide by negative 1.5. Now notice what they did is they brought this negative up to the top, so the d became negative, the 30 became could just write it like this, but it's, you know, when you simplify it, it's kind of nice to go ahead and bring this negative distributed on top. And you've got this now as an inverse function. So we know what the distance between the two is, right? You know that we could figure out how many seconds have passed, because for every 1.5 yards that's gotten less, that's how many seconds have passed. And if we do a composition with this, right, we end up with, we should end up back at t. So if we take the inverse function, plug it into f, so that we take the inverse function, plug it in, 1.5 and 1.5, those cancel, there's a negative here, so that's going to make for negative 30 plus d. 30's cancel. We end up back exactly where we started. So this is, we see that they are inverse functions of each other. And they should be, because that's what we did, is we started with one and solved for the other variable. That's what makes them inverses. How long would it take to catch up? Well, I'm thinking 30, every second it takes 1.5, so 35 by 1.5 should probably get us how many seconds it's going to take. 30 1.5, so that's 1.5 each second, just getting closer. And we get a bit of 20. And again, just more practice. We've got a table. What is the inverse of 3? That means we come and look for the output of 3 and read what is the input. This is an inverse, so we read means the output 0. Here it is. And we read the input. And this is an inverse function. But we start off with g of 2, so this is a forward function, so we start at 2, go ahead and read what the g value is. So here's our intermediate step here. And then now we plug in negative 1 into the f function. Inverse of an inverse, right? So f inverse of 6. So this other stuff, so maybe it's 15. So it makes sense that we're going to look up as the inverse of 6. So f of the output is 6. So it's going to be 2. The answer for this is 2. And so now we're going to do g inverse of 2. Look that up with the g function. We look when the output is 2, what is the input? Erase it all and just verify those answers. Be sure that's what we end up with. And you know, it's always possible that to get an inverse function, it might not be a function itself. So we look at a function of square. So the thing is input of 2 gives us an output of 4, and input of negative 2 gives us an output of 4. What's going to happen is if we try to go backwards, if I start at 4, where do I go? Do I go to negative 2 or do I go to 2? See, this is not a function. The inverse function of, if I put in 4, I would have 2 outputs. So that's why it can't work as it is. Both equal to 4. If I try to do an invert, but I don't know whether I should go to 2 or negative 2 because they're both valid answers. So for this reason, what we do is we restrict the domain to make the function what we call 1-to-1. Each input has only one output. Now, this is still a function if each input has only one output. But for a 1-to-1 function, each output also only has one input. So, um, so what we've done is we basically say x has to be greater than or equal to 0. So this side, we're basically going to erase this stuff doesn't exist. And so now we are 1 to 1, and each output will only have one input as well. So now we know exactly where to go if we code for an inverse function. Okay, so that's one way. If our function is not 1 to 1, we restrict the domain, throw out part of the graph, and say, no, we're going to redefine it only for certain values, and then we've got a function which will have a true inverse function. So what would that function look like? Well, it's a square root function, but it's only the positive square roots. So and as you see, the domain range will change once we domain range of the original function are swapped for the inverse function. Again, we look at this. Would it have an inverse? Well, yeah, it's 1 to 1. And what we use is sort of called the horizontal line test, because each horizontal line only intersects it in one place. So then you'll have it's 1 to 1. This is not 1 to 1. We draw a horizontal line, we get multiple inputs, or these outputs, multiple outputs. So we can't make this. Well, we could restrict it to certain areas, but as it stands right now, no, this one does not have an inverse function. And yeah, you have to break it down where there's, so I could maybe just use this piece, or I could just use the middle piece, or I could use that piece. But those are the three ways I could split it up, but I can't use a combination of the two. I need two of those, because thinking in terms of what's it called? Line test. And for this semester, this part, 3.7, is going to be the next test, so this is where we're going to stop.